There are four historically important gas laws that derive relationships between two physical properties of a gas while keeping the other properties constant. These are Boyle's law, which shows the relationship volume is proportional to 1 over pressure, or pressure is proportional to 1 over volume, where temperature and the number of moles are kept constant. Charles' law shows the relationship of volume being proportional to absolute temperature, when pressure and number of moles are kept constant. Gay-Lussac's law shows that pressure is proportional to absolute temperature when volume and number of moles is kept constant. And fourthly, Avogadro's law, which shows that volume is proportional to the number of moles when pressure and temperature are kept constant. These rules or laws can be put together into a single equation, where volume is proportional to the number of moles times the absolute temperature divided by the pressure. We can get rid of the proportionality sign by introducing a constant. This constant is known as R, or the gas constant. This gives us the equation V is equal to R times NT over P. Rearranged, this gives us the classic ideal gas equation PV equals nRT. This can be rearranged to find P, V, N, or T. But you may ask yourself, how can we calculate the gas constant? To do this, we're going to use some experimental data. A chemist measured the pressure generated at 80 degrees Celsius in a cylinder of fixed volume by different masses of different gases. The results are given below. Show graphically that these results are in accord with the general gas equation. A hint here is that masses of gases cannot be used. We must first of all convert the mass of gas into moles. Once we've done this, we can see the moles and the pressure. We can use this to graph the data for pressure versus number of moles. This data is plotted as a straight line going through the origin. We can see that pressure is proportional to the number of moles N. The gradient is 1100.1. We are going to use this in the following equation. We rearrange the ideal gas equation to show P over N is equal to RT over V. We know that the volume is 2.67 liters and the temperature is 353 Kelvin. We also know that the ratio of P over N is equal to 1100.1. If we place these into the equation, we get the following result, 8.321. This is a value for R, the gas constant. The actual value for R is 8.31451. So why are the different values of R given? If we show the equation R equals PV over NT, we must understand that pressure can be measured in a number of different ways. Consider the case where we have 1 mole of gas at 0 degrees Celsius. We know that it would occupy 22.4 liters. Pressure may be measured as 760 millimeters of mercury, 101.3 kilopascals, or 1 atmosphere. Each of these would give a different value for R. Also, volume could be measured in liters or meters cubed. This gives us a number of values for R based on the volume unit used and the pressure unit used. Let's take a look at some problems using this ideal gas equation. In the first problem, we're asked how many moles of gas does it take to occupy 120 liters at a pressure of 2.30 atmospheres and a temperature of 340 Kelvin. We write down the ideal gas equation and rearrange for the unknown, in this case N, the number of moles. Please note that because the pressure is in atmospheres, we're going to use the gas constant for atmospheres, which is 0.08206. Once we've substituted in the values, we can solve. The least number of significant figures in this particular problem is 3, so the answer is given to 3 significant figures. In this type of problem, we're not given the number of moles, but we're given the number of grams of hydrogen. In this case, it's contained in a 2.00 litre container at 20 degrees Celsius, and we're asked what the pressure is in this container in millimeters of mercury. We need not use the gas constant for millimeters of mercury. We can solve this using the gas constant from the previous equation and then change to millimeters of mercury at the end. Once again, we write down the ideal gas equation, but this time we must calculate N from the number of moles, and we work out 1.09 divided by 2.02, giving us 0.540 moles. We substitute this value into the equation, and again we're using the gas constant for atmospheres. We solve and we get an answer of 6.49 atmospheres. However, the problem asks the pressure to be given in millimeters of mercury. We multiply atmospheres by 760 to get the answer in millimeters of mercury. Once again, there are three significant figures. In this problem, we're asked what volume will 1.27 moles of helium gas occupy at STP. We use the ideal gas equation and rearrange. We substitute in the values and we get an answer of 28.5 litres. You may be thinking this is easily done by simply multiplying 1.27 by 22.4 litres. Would it make any difference in the answer if the gas were oxygen, krypton, carbon dioxide or methane? And the answer in each case is no, no, no. The exact identity of the gas makes no difference to the number of moles present. By the way, note that since the temperature and the pressure would be the same volume will contain the same number of molecules of gas. This is Avogadro's hypothesis.